Ladies and gentlemen, it's a pleasure for me as rector of Universidad Politécnica de Madrid to welcome Professor Gerard Mourou. It's an honor for us to have a Nobel Prize in this room, Carlos Vera, of our Industrial Engineering School of our university. Sure that the conference that will be coming later will be, well, you can see a lot of people here, professors, researchers, personal students that are waiting to your speech. So thanks for coming here and for giving us this speech and for sharing this day with us. It's a pleasure. So, before starting the conference, different members of the table will say a few words. And first of all, I hand over to Professor Perlado, José Manuel Perlado, is the director of the Instituto de Fusión Nuclear Guillermo Velarde. Manolo, are you somewhere? Yes. And we're on the right. Please, Manolo.
Gracias, rector. Señor rector magnífico, profesor Gerard Mourou, Premio Nobel de Física 2018, señora directora general de Investigación, Desarrollo e Innovación del Ministerio de Ciencia, Innovación y Universidades, señora vicerrectora de Investigación y Doctorado de la UPM, señora directora en funciones de la Escuela Técnica Superior de Ingenieros Industriales, señora consejera científica de la Embajada de Francia y señora encargada de la misión científica del Institut Français, querido Pedro, autoridades de muy diversos ámbitos, por hacerlo así un poquito corto, señoras y señores, Madame et Messieurs, je voudrais parler aujourd'hui dans la langue de Molière en hommage de notre invité, le professeur Gerard Mourou, prix Nobel de physique 2018. Cher professeur Mourou, c'est pour nous un très grand honneur de vous avoir ici aujourd'hui à notre université, à notre école, à notre institut de la fusion nucléaire. Je me souviens maintenant des temps que nous avons travaillé avec vous, poussant votre idée, votre projet, le Streamlight Infrastructure, que maintenant c'est une absolument réalité à l'Hongrie, Roumanie et la République tchèque. Il y a des institutions espagnoles scientifiques qui veulent encore aujourd'hui avoir une quatrième partie ici à l'Espagne. Je le dis ça à propos de notre autorité qui sont ici. Une installation qui ouvre de nouveaux horizons dans la science et dans la compréhension des lois de notre univers. Je suis bien sûr que les relations entre notre institution scientifique seront encore plus renforcées après votre visite. Cher Gerard, avec toute notre amitié, merci et bienvenue.
Thank you very much. So next turn is for our deputy director of the school, is Professor González Fernández. Camino, please.
Thank you. Gracias. Gracias. Thank you, Rector, Profesor Mourou, Profesora Teresa Riesgo, Asunción, Manolo, representación de la Embajada Francesa, academic authorities, professors, staff, students, and welcome everybody here. It's a great honor for me to welcome Professor Mourou to our school on behalf of our director, Professor Oscar García Suárez, that can join us today. Professor Mourou, please consider that this school is your home, and let me introduce it to you. Our school is very large. We have more than 4,000 students, 400 teachers, staff, and many enthusiastic research. So today I would like to emphasize two aspects of our school. I will be very brief. The first one is our potential for the research. We are currently participating in many international research programs, and we have brilliant scientists working in them. Secondly, our school is very internationally oriented. We have much connected with other institutions, universities, for instance, with l'École Polytechnique, you know. Particularly professors and scientists from the Instituto de Fusión Nuclear combine in the best way these two aspects. Passion for the research and internationalization and strategic line of this work. At this point, I would like to thank Professor Perlado and all people from the Instituto to give our opportunity to hear Professor Mourou here. And thank you very much, Professor Mourou. Thanks for sharing your knowledge with us. This is a special day for our school. You can see all people here hearing from you. And we have the great opportunity to learn from a Nobel Prize. We are now very much looking forward to hearing your lecture. Welcome. Merci beaucoup.
Thank you very much, Camino. So now we hand over to our DG for Research, Development, Innovation of the Ministry for Science, Innovation and Universities of the Spanish government. By the way, she is as well professor of this school, Professor Riesgo. Teresa, please.
Thank you very much, Rector. Professor Mourou, it's really a pleasure to have you here in this school, in this house, that, as I told you, is my alma mater. So for me, this is being at home. In the name of the Minister of Science, Innovation and Universities, who could not do it today, I want to welcome you to Spain and to tell you that our ministry is very much encouraged to enhance the cooperation with the large installations that you are running and you are promoting very much in Europe, and also in cooperation with the installations that we have already in Spain, like the Centro de Láseres Pulsados that I see it's a director here in this audience. That I thank you very much for coming. I would like also to highlight the importance of the research that is being done here in this school, particularly in the Institute for Nuclear Fusion that is run by Professor Perlado, and that I understand that you know well. But I want to say that in this small place like this school, I said, in the center of the city, many of the research activities that are being done in the area of fusion and the new energies that are about to come are here for, are very much intensive research done here. We are very much looking forward to your words and to learn from your passion for light. So thank you very much, Professor Mourou, for being here. And I hope that you enjoy your stay in Spain. So thank you very much.
Well, thank you very much, Teresa. So now Professor Pedro Velarde will provide us an introduction for our speaker, for Professor Mourou. So please, Pedro.
So, dear students and colleagues, it's my pleasure to introduce Nobel Prize winner, Professor Gerard Mourou, that is going to talk to us about the passion for extreme light, the mysteries and the effects of the light to extreme intensities. I want to, something is going on. I'm going to highlight two things about Professor Mourou. One is about the well-known achievements of Professor Mourou. There is something that I would like to draw to your attention. that one is having a lot of influence throughout Europe. Is the so-called Extreme Light Infrastructure Project, or the code name is ELI. The Professor Mourou started this project in the early 2000s. Nowadays, this project promotes 3 ultra-high intensity lasers in Europe, with applications from range from, let's say, secondary sources of particles, attoseconds, light pulses, gamma ray intense sources, and extreme high intensity, let's say above 10 to the 23 watts per square centimeter. To have an idea of this number is almost 2 times higher than put all the power of the sun put through 1 square meter in surface. So it's extreme high intensity. So, but one of the initial meetings of this project, before it was presented to the European authorities, took place right here, this school. In fact, in the photo, you can recognize some of the people that who are here now, just now. Finally, I wanted to highlight the Professor Mourou's passion for art, for the relation between art and science, and his collaboration with the Louvre Museum in study the hidden layers within various paintings. So, ladies and gentlemen, Professor Mourou.
Well, I'm really speechless in front, of this large audience, also in front of my colleagues, that helped me a lot, I have to say. You were mentioning a lot about these extremely light infrastructures. I want also to thank, of course, the rectors and the representative from the ministry and so on. Okay. So I'm very humbled by all that. And so I'm going to talk to you about what led me to get to this Nobel Prize, and also I want really to acknowledge the fact that it is also by the help of people like Manuel Velardo or Pedro Velarde, but I think this field also has made some significant steps. So I'm going to talk to you about extreme light and this passion I have for extreme light since some time now. And also I have to say that I'm not going to give you my standard presentation, because my standard presentation usually is for the general audience. But this morning, I understand, in Polytechnica Institute here, I have really a much more knowledgeable audience, so I will go a little bit further into the technical details. So anyway, before I'm going to talk about very high intensity lasers, and everything started with my co-laureate, Donna Strickland, about 35 years ago, okay, when we demonstrated this concept of this technique to increase peak power, laser peak power, by an enormous jump. And here we are, both of us, in Stockholm. I have to say that when I got this incredible phone call that I hope many of you
will have a chance to get ones. But this is always happening on the first Tuesday of October. When I got this phone call, I was going to the swimming pool, and when my secretary, Cathy Sarrazin, called me, and they said, you got this call from a foreign country. And it was around 12 o'clock, so this is usually the time where you get this phone call. And so when I pick up the phone, I had the chairman of the Nobel Committee for Physics, and who told me, it was Larsen, Goran Larsen, and who told me that I got the prize. And he said, I'm very, very pleased also to tell you that you are going to share it with Donna Strickland, your former student. And I was very, very, of course, very, very high, elated by this news, because I knew that Donna was, there are very, very few women who got this prize. And Donna is the third woman who got the prize. There's over 200 men who got the prize in physics, but she was the third woman behind Madame Curie and Maya Gopper. This is it was a great honor. Of course, we shared this prize with Ashkin, for his discovery of the light tweezers. So anyway, I'm going to talk to you a little bit about high intensity. As I say, it's not my standard presentations because there is many knowledgeable people in this audience, so I raised up the level. Okay, so everything started with this invention, and this invention is about how can we really boost the the intensities and of lasers. So we know that we can produce short pulses, but in a relatively low energy range. And so what we want to try to do is to amplify it. And but for instance, here I show that you have a short pulse, and you cannot take directly the short pulse into these amplifiers, and just like that, okay? Because as you amplify the pulse, you are going to destroy first the wavefront of your beam, which is very, very important, and second, if you go beyond that, you are going to destroy your material, your amplifier, and which is very expensive. And so you want to avoid this. So, and that, you will see later that that really clamped the laser peak power to some level. So in order to avoid these problems, with Donna, what we've done is we stretch first these short pulses to a relatively long duration, nanoseconds when you start at sub-picosecond in those days. And then when the pulse is stretched, of course, its intensity is much less. And then you can amplify it and extract the energy from your amplifier nicely and safely, and you get an amplified pulse. And usually, we amplify it by 10 orders of magnitude. Here we have only maybe a factor of 2, but the amplification is around about 10, 11, 12 orders of magnitude, so huge amplifications. And so when you have extracted this energy, what you can do is you are going to compress the pulse. We are using, to stretch and compress pulses, we are using dispersion technique. In this case, it's using a pair of gratings. I'm not going to go into details. So when you compress the pulse, then you manage to get all the energy of this amplifier into these short pulses, and you get this enormous peak power. So that, of course, that opened opened the door to many, many applications. So just to remind you that we can produce, this type of power, petawatt pulses, because we are able to, and 10 petawatt, I heard that someone said it already, but it's about, petawatt is about 1,000 times the power of the world grid power. It's about 1,000 times. So it's very, very significant, and of course, and we do that only, by doing millions of billions of a second, of course. Okay, that's the trick. And so here is a little bit of graph that shows the intensity of lasers expressed in watt per square centimeters as a function of here. So first we started in 1960. The first laser was demonstrated, and that was done by Ted Mehman. And at that time, the power was of the order of the intensity was in a range of 10 to the 8 watt per square centimeter. Then quickly, we were able really to raise this intensity to a level in a range of 10 to the 14, 15 watt per square centimeters by using some techniques. But then we had a plateau, and this plateau, as I mentioned, this plateau is due to the fact that you are at the limit of the damage threshold, to reach the damage threshold of the optical component. So you have to stay. And so we stayed there, and until we came to CPA, and the CPA, with the CPA, we, were able to climb now this curve and go much, much higher in intensities. And just so you can appreciate, we made a jump of more than 5 orders of magnitude, okay? And we hope by with the in the extreme light infrastructure project, but also with laser like you have in Salamanca, under the directions of Luis Rosso, we could really go to this level. Okay, so we will be able really we will have increased the intensity by 10 orders of magnitude, which is, of course, a large number. It's 1 billion times. So now I'm going to also introduce. I'm sorry, I will go back a little bit. Yeah. So now with the 3 infrastructures that we are building here, we are at this level, and I will also describe ways to go much higher. Okay, in intensity. So these are introducing, these 3 beautiful infrastructures, which are in fact under one management, okay, which is Eli DC, and so one is in Czech Republic, the other one is in Hungary, and the third one is in Romania, okay, and they are all petawatt facilities, but the petawatt laser have different flavors. But they are all petawatts. Okay, now the thing which is remarkable about the CPA is because before CPA, we had the only thing we were doing, we were only capable with conventional lasers to study atomic physics, okay, because you were not able really to go to very high intensity. So atomic physics, of course, is really the physics of the electrons which are moving around a nucleus. Here you see the nucleus, very small, and the electrons, okay? And so atomic physics is a study of this, and molecular physics also. But so now, because of the fact that we can really increase the intensity, we can go from atomic physics or EV physics, I would say, electron volt physics, and to GeV and hopefully TeV physics. Okay, so this is really a considerable step, considerable leap forward, okay, or upward. So we are going to talk about that. Now, I said that because this audience is more, has higher level of knowledge, so I can really go a little bit further. And I will talk technique to go really beyond. I'm interested to go beyond the horizon, okay? And so I will here talk about technique to reach pulses very short, now in the femtosecond, but attosecond and maybe zeptosecond, okay? So every time, of course, every time when you find a way to shorten the pulse, then you find also the way to increase the power, okay? So this is really, instead of increasing the energy, which is a very, very expensive proposition now, then the only way to increase the power is by decreasing the pulse duration. So that's the reason that you see that instead of working with pulses like 30 femtoseconds, about you have about 15 optical cycle. Okay, we would like now with our developing technique to produce only one single cycle. Okay, and get into the 2 femtosecond regime. But now a 2 femtosecond regime is still too long for us. Okay, and so we are pushing into the atto and zeptosecond regime. Atto is 10 minus 18, zepto is 10 minus 21 second, okay? So of course it's challenging, okay? But in order to do that, you will see that we have to compress pulses in the X-ray regime and also gamma ray regime. Now, if you are able to do that, okay, then fabulous applications are coming up. And so, for instance, you can really now produce accelerations or produce accelerate particles in the TeV regime. And this TeV can be produced over only a centimeter. Remember that a TeV machine is LHC, Large Hadron Collider at CERN, but it's 27 kilometers. Okay. Now we have the hope to produce TeV over centimeter scale systems. Okay. And what also we can do, we can reproduce relativistic protons, which is very, very important, beautiful application, for proton therapy and also for nuclear fusions. For nuclear waste treatment. And you can also think about doing tabletop cosmology, and finally we will have to say one word about high average power. I'm not sure I would be able to reach this point here, but So let's start with this, the first thing about compression of pulses to the single cycle regime. So as I said, right now, the pulses are in a 20 femtosecond, 20, 30 femtosecond range, which, the period of light is 2.5 femtosecond in this wavelength regime. So you see that we are talking about having about 10, 15 cycles, okay? So now you would like to get only one cycle, okay? In order to get only one, that is, we have to compress the pulse. What we are going to use the fact that we are going to produce some self-phase modulations. And the self-phase modulations is due to, we can do that because the intensity, the index of refraction is intensity dependent. So when you have a pulse which is going through this medium, you are going to change the phase during the propagation of the pulse, and so you are going to broaden the spectrum. You are going to generate frequencies and broaden the spectrum. So if you have larger spectrums, then you will have the capability now really to compress the pulse. Okay, so a technique like this has been developed, but for pulses with low energy. Okay, low energy, I mean nanojoules. Okay, and then that was the original work. Okay, using fibers, and then now people like Svelto and also Horacio Svelto and Krauss and so on demonstrated that we could also do that with capillaries, and the capillaries you are able now to compress pulses at a millijoule level, okay, to the single cycle regime. But this is not enough for us, okay? We want to compress pulses to the single cycle regime, but now pulses at a joule, 10 joule, 100 joules level, okay? And this is, so we had to develop this technique to do that, which is based on the fact that at this level, for high energy lasers, they provide not a Gaussian beam like we do with conventional lasers, at low energy, but they provide flat top, beams, okay? Beams with intensity which is uniform across the beam. So what we could do is could think about producing this self-phase modulation on relatively thin specimen, thin plastic plate maybe, like that, okay? Because you have the possibility, if you're shining the pulse into a plastic plate like that, you will be able really to produce the self-phase modulation that you are looking for, as well as the group velocity, in order uniformly. So then after, you can really compress the pulse. So now the type of lasers that are providing petawatt systems, and it's just, Salamanca are doing it also, but you have commercial systems. And so they are not very big, I mean, they're sizable, but they are not very, very big to really provide this type of power. And so you have one. And what is important is the fact that the output of the laser is flat, okay? It's really flat. I mean, these are the early days system. Now it's better, okay? So it's relatively flat. The pulses are uniform in intensity. So if you have a pulse like this coming out from your laser, petawatt pulses, so you have typically 10 joules, 100 joules, okay? And not millijoules like we have been done now. They are about 25 femtoseconds. So we go into a first film where we are going to produce some cell-phase modulations. And also, because you have a broad pulse, you are going to have group velocity dispersion. And then you end up with a pulse which has been stretched and with larger bandwidth. And if you compress these pulses at this level, you are going to get something like 5 femtosecond pulses. 5 femtoseconds, about 2 cycles, 2 or 3 cycles. And so you repeat that again into a thin films. And again, the thin films are going to produce cell-phase modulation, group velocity dispersion. And you are going to have a broader pulse that you will be, and with a chirp, and that you will be able to compress with what we call chirp mirrors. And then you have pulses at 2 femtoseconds. So this is what we are demonstrating, and it starts to look very good. And what's this? That was an idea that we patented some time ago when I was at LOA. And so okay, so here you have the result. You start with a 25 femtosecond pulses, and now you compress it with double stage compression, and then you get a single cycle pulse here. So of course, because this type of compressor is very efficient, so you off the bat you get something like 10 times or so the peak power. Okay, so this is a nice way to get the peak power. Now what we have to do is so if you have a single cycle pulse like that, you have, of course, new opportunities, and also what you like to do. So here you have a single cycle. You like to compress the pulse even shorter, and so there is one way to do it, and it is ready to use this single cycle here, and you irradiate a target which is composed, of course, of ions, of electrons, and so on. And this pulse is going now to really, because you have a very, very large pressure, or relative pressures, huge pressures, so the pressure is going to move the electrons in front, but you are going to have the ions, which are more massive, behind, like this. Okay, so you have the electrons in front here. So this is you move the critical surface, okay, inward, and then you are, and the ions which are in the back. So you are basically establishing a huge DC field, okay? And this DC field is going right now to play and attract the electrons and move the electrons now forward, you know, very, very efficiently, and basically at the speed of light, okay? These electrons will move at the speed of light. So what you are doing is exciting, because you have basically a moving mirror moving at the speed of light. So when you have a moving mirror moving at the speed of light, what you are getting is, so because this light is coming at the speed of light, of course, the incident light, okay? Now, the light which is being reflected will be reflected at the speed of light, of course. And so the only way, so what's going to happen is this is going to lead to a compression, okay? To a compression which can be extremely significant, of course, as you will see, as Natalia Nomova showed it some time ago. The compression, of course, will be a function of the intensity of the pulse, okay? Was what we call the normalized vector potential, A0 here. And you see that as you increase the intensity, as you increase A0, then you decrease the pulse durations, and typically there's a relation that she was able to establish, 600 attosecond over a naught, which means that now with very, very large intensity laser, with a naught in a regime of 100, maybe 1,000, okay, then you can get pulses in a single attosecond and sub-attosecond, which means zeptosecond. And yeah, here we pushed a little bit the simulations, and at 10 to the 23, you would expect something, of course, like a single zeptosecond, but I don't really believe that. But it's just to show you that we now can contemplate, pulses, X-ray, or even gamma ray pulses at this level. And so this is very nice, because if you are compressing the pulses to this incredible pulse duration, very short, 10 minus 21, if you have only 1 joule, okay, which is nothing, because I like to say that for your breakfast, you had million joules, for your breakfast. And so 1 joule in a zeptosecond, it means that you can produce zettawatt pulses, okay? 10 to the 21 watt, huge. Now, also, you will see that you will be, because these pulses, these high-intensity pulses, okay? Because right now we're only talking about high-intensity pulses in the visible, but now these pulses are going to will be high-intensity in the X-ray regime, which is completely, of course, very, very different. And so if you do that, you will be able really to accelerate particles with an enormous gradient. And because if you have X-rays, you will be able not only to use gas for acceleration, but you are going to use solid. I will show you that. Okay, and of course, because now if you take this zettawatt, you can focus it on the lambda. It's going to be a little bit, lambda is, I hope that Philippe Zetoun will help us a lot for that, focusing X-rays over lambda. Then if you do that, you will reach rapidly a level of intensity in a range of 10 to the 29, which is what we call the Schwinger field, where we materialize the vacuum and light, okay? And this is, in fact, one of the very important goals that we will likely to achieve with ELI. So at this regime, you turn light into matter and antimatter. So now, how can we accelerate accelerate particle with light? Well, the original idea came up from Toshi Tajima and John Dawson in '79, and they are going to use really just a surfing method, Here, the electrons are going to surf on the wave, on the plasma wave produced by the laser. That's it. And we have shown that it's a very effective way to do it, okay? Very efficient way to do it. So it's very simple. You take the laser pulse, which is very simple. It's amazingly simple. And you focus this laser pulse into, say, a gas jet, okay? And so what you do is you are going to ionize the gas jet and also create a plasma, okay? This gas is a gas jet. The density of the gas jet is typically in a range of 10 to the 18, 10 to the 17 watt per square centimeters. I'm sorry, no, this is the density, I'm sorry, the density is 10 to the 17, 10 to the 18 particles per cubic centimeters, okay? And you can get GeV per centimeters. Now, the trick is, the new twist, you know, that I would like really to promote here, is the fact we are now going we are not going to use gas, but we will actually to use solid. Why? Well, because the solid, of course, has very high electron density, 10 to the 23, okay? So you change things by 5 order of magnitude, and you will get, we should be able to go into the TeV regime. But if you want to do that, of course, because you want really to have this X-ray regime that you are going to use for Wakefield accelerations, this X-ray has to go through solid. So, I'm sorry, the light has to go through solid, so it has to be X-rays, okay? And short. So this is, what is fascinating is that, you know, the energy gain, when we do Wakefield, it goes this way, okay? The energy gain is equal to A0 square, I mean, the intensity of the normalized vector potential square, and not C square. But there is this factor here, which is very, very important. It is MC, critical density, over NE, the density of the electrons in medium. So when we are dealing with light, this is all the work which has been done now with light. The critical density is, for 1 eV photons, about 10 to the 21 electron per cubic centimeters. And so the critical density is 10 to the 21. So if you really want to have this ratio very large, okay, you have to have a very low NE, okay? You want to have a very, very low NE. So, which means that you have to work with low density gas. And this is what is happening now, okay? Now, if you are, let's suppose that now you move to solid, then things changes, of course, dramatically. Because now this NC, and if you have the X-ray, the NC now is 10 to the 29, okay? And instead of 10 to the 21, okay? So a huge jump. And and because N solid is 10 to the 23, so you have this ratio now is 6 orders of magnitude. It's typically 3 orders of magnitude than in this, if you are using visible light in gas. 6 orders of magnitude, which means now you are in a TeV per centimeters. So now if you look at the CERN, LHC, you know that the particles are really going at TeV. Well, it's 27 kilometers, okay? And so, because you are using radio frequency, you know, microwave radio frequency. Well, it's in gigahertz. And so this is the field, the gradient field is such that you need 27 kilometers to get to the TeV. But of course, if you are using laser Wakefield in the visible, that is what is being done now. I mean, you can think about building systems with 100 meters in dimensions, which is of course an enormous gain. But of course, now if you do X-rays, as I say, you have 10 to the 3, you have TeV per centimeter, so it will be something which will of that size, okay? So, of course, something which is incredibly fascinating because the applications are huge. And you know, this is amazing when you think a minute. You know, before when the laser, when the field started with Van der Graaf, you know, and with Van der Graaf, it's basically a zero, it's a DC field, okay? So zero Hertz, you know, and then you are getting MeV, total energy. Now, in order to boost this field, you went to RF cavity at 10 to the 9 Hertz, gigahertz, and you are getting MeV per centimeters. Now, with light, you go from 10 gigahertz, 10 to the 9 hertz, to now almost petahertz, okay? And then you are going, accordingly, you are going to change things by another 3 orders of magnitude. So it's natural to think that if you want to get to the next step, because this is in a visible, you have to move to the X-ray regime and trying to do, if you move high field in the X-ray regime, something that we don't have now, of course. And so this will be absolutely fantastic. And if you're really into the X-rays, you move from 10 to the 15 and to 10 to the 18, and you are in a TeV per centimeter. So this really gives you an idea where we want really to move. It's already nice, you know, to know, even if what I showed you is very, you know, back of the envelope, you know, calculations. Nevertheless, it gives you the general idea. And then, if you have, because if you have, of course, TeV per centimeter, you can produce PeV now, relatively fast, which is absolutely, there's no way we can produce PeV on Earth right now, okay? So you can really start to study, for instance, do some cosmic physics, study particles, high energy particles, but now this time, these high energy particles, they are not only produced in the cosmos, but they can be produced on a table, or a big table, but on a table. Anyway, so this is very exciting. Also, if you have zeptosecond pulses, gamma rays of zeptosecond pulses, then you can use that really to study gamma ray burst, you know, and study over very, very short distance, because now you are really looking at gamma ray burst, which has been produced 1 billion years ago. So this is, of course, now this is a distance between, is very, very long, of course, and you could now, because you have a very, very short pulses, gamma ray bursts, you know, have typically durations of maybe minutes, seconds, something like that. But now, if you have this very, very short pulses, you can do the metrology of your short pulses, you know, on a much shorter distances, and so you can really try to understand the cosmos and study Lorentz invariance on the table, which is, of course, incredible. So the other thing which is exciting, okay, if you are able now to produce very, very short pulse in a single cycle regime, you can produce protons very efficiently, okay? High energy protons, relativistic protons, GeV protons. And it will be, if you had a very, very short pulse, you can really now whack a single thin sheet of materials, metal or dielectrics, and then you can really now push the electron forward, leave the proton backward, and so you have the electrons now which are dragging with them, you know, these protons, and so you can produce protons. We can demonstrate that protons, I mean, by simulations, protons at a GeV level. You know that, of course, it's very, very I don't have it here. But it's very difficult to accelerate protons, you know, and it takes usually very, very large machines. But if you are single cycle, then it's relatively easy to, it should be very easy to produce these electrons. You know, and you can show that if you have a long pulse, which is long pulse, I mean 16 cycle pulse, about 20 femtosecond pulses, then you know, it takes a significant amount of energy and so on to produce relativistic sub-GeV pulses. If you go to 4 cycle, moving from 16 cycle to 4 cycle, things improve much better, okay? And then if you go to 1 cycle, then immediately, you know, you get into this GeV range for protons, okay? And so this is really very important to move into now into shorter and shorter and shorter pulses. And for me, I've always been like that, you know, since the very, very beginning, okay? And I had a chance to be involved in this very beginning. You know, we always found that every time when you can shorten the pulse, then things improve. So this is, I think this is what we would like really to do, is really to shorten the pulses in order to do this particle acceleration, particle production, and so on. So now I'm going to list some of the applications with extreme light. You know, of course, scientific applications. You know, what's exciting, you can have laser astrophysics and cosmology. I just go. One thing also I just mentioned very quickly is you can now to look at vacuum polarizations, materialization of light, you know, going into the Schwinger field and so on. And you could even go beyond the standard model, you know, X factory, you know, you could think, because it takes only 150 MeV to produce them, so it's not very difficult. We look at dark matters and so on. In societal application, and that is something which is very important for us, and you know, we have to have really societal application. I think we are scientists, we are blessed because we are getting this money for society to do something we like, we love, okay? So we have to give back. We have to give back, and here, you know, for the extreme light, we could really do things very exciting, like, for instance, a transmutation of nuclear waste, okay? Nuclear pharmacology, proton therapy, you know, and so on. Okay, and so this is some of the applications here which are really displayed here. Proton therapy, okay, here. You know that if you have high energy protons in a few hundreds MeV, there is something very, very nice about proton as opposed to X-ray. If you want really to burn a tumor with X-rays or electrons. What the problem is, if you really have to penetrate into bulk of the tissues in order to reach your tumor, then you can burn the tumor, but also you are going to affect, burn also to some extent. You are going to burn also the tissues, the healthy tissues which are in front. Okay, but if you have the protons, all the protons. This is amazing. Is the protons, you know, stop basically at a distance which is called a Bragg peak. Okay, and so you can adjust this distance, you know, quite easily by adjusting the energy of the protons. And so all the light is, I mean, all the energy is deposited now into the tumor and not in the healthy tissues. So this is, of course, very, very nice. Now also you can, with the high energy protons, you can produce high energy neutrons, and you can also make radionuclide. But you can put them in pellets that you can really put in tumor, inject into a tumor of a patient, and then the nuclide will burn the tumors. Okay, and of course, there's a lot of application now, in diagnostics. Okay, we all, heard about PET scan and so on. Finally, you have applications that, of course, I think it's very important because I think we could have a shot at it, and it is really trying to treat the nuclear waste, okay? Because, of course, nuclear energy is certainly something which is maybe the best energy to produce. We don't have to destroy the planet, to produce the energy. But the problem, of course, is we have, after that, to deal with the nuclear waste. Okay, and so the idea to clean the nuclear waste it will be, since now we know how to produce neutrons, we can use these high energy neutrons really to fission the nucleus of minor actinide, okay, which are really the bad guys, the 4 bad guys, curium, neptunium, americium, and plutonium. So we can reduce the nocivity, the time for nocivity, from 100,000 of years, maybe million years, to a single year or few years. Okay, so of course that will be extremely nice if we could do that. But I think this now, because what we can do with CPA, we can really now, and with all the work I showed you, we can produce high energy particle on a compact size with equipment that even we can move. For instance, we could move an accelerators, maybe a GeV accelerator or MEV accelerators for nuclear waste instead of moving the waste. Okay, so I'm going to stop, to conclude now by saying that in the spirit of the Nobel, Alfred Nobel, motto, will be, in conclusion, extreme light is capable of generating the largest field, the largest acceleration, the largest temperature, and the largest pressures. And it carries the best hope and opportunities for the future of science and society. Thank you very much. So I don't know, do we have questions after this? Or we, yeah, okay.
Thank you very much, Professor Mourou. It's encouraging, and particularly for our students, it's an opportunity, a very good opportunity. And so what I would do, because...
I would like to add one thing. It would be nice if also women could really ask the questions.
Indeed.
Not just men.
Indeed. So, absolutely right. But I'm going to propose, by the way, would it be possible to switch off that strong light, please?
That would be nice.
Hi.
Oh, that's even better. Oh, that's
better.
nice. That's wonderful. Thank you. Professor Mourou has 4 questions. We had foreseen something in this line. We have a very tight time schedule now due to the organization of the event. And then what I would invite is you, as I was going to say 5, but attending to this question of Professor Mourou, let's say 6. So it's even number. 3 men, 3 women, 6 questions. You select all from students, because the opportunity is for students. And the 6 questions, you collect them, you collect them, and Professor Mourou answers all of them at once, right? Okay, so 6 questions, blah, 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 and then a common reply to all of them. So it's your choice. Please raise hands.
¿Alguien que... ¿Nadie más quiere
Students
preguntar?
raising hands.
¿Preguntas? ¿Quién tiene alguna duda o le quiere preguntar algo a Gerard Mourou? ¿Se me oye? Sí. Ya, aparte de él, no hay nadie más. Tenéis 5 más, así que... Y además es chica, así que a lo mejor le podemos dejar.
Let's see if there are 6 students, and then if there are not 6 students, then the faculty as well. Thank you.
Pablo.
It's the opportunities for everybody,
Pablo.
students, for faculty as well. All right.
Mándamelas por WhatsApp las preguntas mientras las van haciendo, ¿vale?
So 1 student and 2 students.
Hello.
Excuse me, the term should be closed. So 1, 2, only 2 students to make questions.
Supongo que se irán animando mientras pregunta él y el otro ya irán levantando la mano, ¿no?
No, because the questions should be 1, 2, 3, 4, 5, 6, and Professor Mourou replies to all of them. So 6 hands.
¿Alguien se anima? Venga, 6
3
manos.
men,
Levanta la tuya.
3 women.
Levanta la mano. ¿Quién más quiere preguntar? Ya tenemos 2, nos faltan 3 chicas. Vaya, qué casualidad. Chicas, ya tenemos otra. ¿Una? Sí, ¿no? ¿Tienes duda? Vale. ¿Ninguna estudiante quiere preguntar? Pues entonces...
Faculty, please.
Vale. Y nos faltaría otra chica más. Venga, la cuota de género. ¿Vale? ¿Nadie? No veo a ninguna chica levantar la mano. Así que tenemos 5. ¿Nos vale? Venga, pues
You know,
ahora
we
me
can
seguís
invite
diciendo quiénes
somebody
sois, ¿vale?
Um, so thanks for an interesting talk. Yeah, it was much easier to understand than reading the Wikipedia page, first of all. So my question is a little bit less technical, but more about like the project. Can you say a few words? How did it start? How did you come up with the idea? How like the cooperation? Like, did you work also only with your partner, or was there more people involved? And I don't know. Yeah.
Thank you. Second question.
Hi, thanks for your talk. You talked today about the fundamental limits in the search for the shortest light pulses. Do you think the other lines of research about other fundamental limits in light, like the phase or the state of polarization that are being investigated, could throw some light into that aspect? Thank you.
Thank you. So third question, please.
Okay, I'm a professor from Universidad Complutense in Madrid. I'm interested in the subject of human resources, in the sense that does Europe have the capability of generating educated people to attend all these installations, to take care of all the centers, and what is the role of Spain? Should we do an extra effort to educate students for the field? Thank you.
Yes, please. You are not a student, but...
Yeah, well, I'm not a student. No.
Okay.
Can you hear me well?
You look like a student.
Good.
Thank you.
Please.
I'm a particle physicist. So my question is the following. I would expect that very high energy photons would create pairs, proton-antiproton pairs, but you haven't mentioned at all antiprotons, so I'm a bit puzzled.
So this is the fourth question. Thank you very much. The fifth one.
Falta uno, que le he perdido la vista. Ahí está.
Well,
my question is more technical, I think, and it's about the light generation in the crystal after the pulse. If you could explain it a little better, because I would like to understand more the physics about it, even if it's just in a paragraph or two.
No, could you repeat your question? Because
in the presentation, you showed that by the high energy pulse, you could generate the
high power
pulse. You could produce a higher energy radiation from passing through a crystal.
Yes.
Could you explain that a little better? Because I would like to understand that a bit.
You are talking about the compression, relativistic compression.
In the
yes.
Thank you very much.
Now the last and sixth question. No question.
¿Alguna chica se atreve? Ay,
There is room for one question.
Te dejamos. Venga.
Oh, you are not the women. Indeed.
Hello, Professor. Thanks for coming here to give us this talk today. I wanted to ask you, during your research, was there any single point, like breakthrough you found that actually made it possible, or was it more of a gradual and incremental process? Thank you.
Well, any question else from a woman? Because Professor Mourou wanted the women. So there is room for you for a second question, if you want. Our faculty, do you want a question else? No, you colleague. There is room for one question else. Do you want a second question? No, thank you. So these are 6 questions then. Thank you very much.
Sorry, it's my turn now.
Professor Mourou.
I will try really to make my best, try to link these questions, together. So the first was, of course, the idea of the CPA, how it came about, and if we had, more people involved and so on. It came about because I was at the University of Rochester at that time, and I was working on trying to produce short pulses with what we call dye lasers. We don't see any dye laser now in the lab, but that's what we were using at that time to get short pulses. And short pulses was sub-picosecond, okay? Not femtosecond, sub-picosecond. And on the other hand, I was also in the same laboratory, which was a very big lab, laboratory for laser energetics in Rochester. They were really developing very, very large-scale lasers for laser fusion applications. And these lasers were neodymium glass lasers. And they were really, they were really, doing a very, very good job in terms of engineering these very, very large systems. So I learned about what we call the B integral. The B integral is really the amount of non-linearity that you are producing in your beams because of the intensity, because of the intensity-dependent index of refraction. And so we, because of the B integral in glasses, you couldn't really get very short pulses in glasses. But you had a lot of energy stored in the light, but you couldn't really extract it because you will damage the material. The other hand, for the dye lasers, you can only extract very small amount of energy. So you are always safe, basically, okay? So that's the reason why in those days, you could amplify only short pulses in dyes and not in material like glasses, which has a lot of energy, And so that was a game. You say, how can I extract this energy from the glasses, And I know that we couldn't do it because of the index of refractions, which was dependent on the intensity, but then I thought about maybe by stretching. By stretching, we could really get the pulse long without changing this energy and extract the energy and try to compress it. So at that time, Donna Strickland was looking for a thesis. So she knocked to my door, and she would say, well, I want ready to do a thesis. In fact, she knew my laboratory, because at that time the laboratory was dye laboratory, and they were beautiful because you have all these colors. And she was attracted by this. And so she asked me if I had a thesis topic for her. And I said, yeah, it just came, this idea to extract, to make short pulses, trying to amplify it, and stretch it, amplify it, compress it, and blah. And she said, wow, are you sure this is going to be enough for my thesis? And I said, well, I think so. She got a Nobel Prize with that, with her thesis. So that was new. And at the beginning, and very, very few, you were asking me if we had a lot of people working on it. No, I mean, we were only few, Donna, myself, and maybe other students in my group involved, and not many. It took really some time for the field to take off, really, because it was so different from what we were doing at that time. At that time, as I said, it was neodymium glass and dye lasers, and that's it. Okay, and so it was a completely different idea, and so no people really dare to do it. It's amazing now when you think a minute. Okay, the second question is, do we have a limit, in the shortness of the pulses? And the question is, depends the wavelength. Of course, if you are in a visible, of course, the light is going to be limited by one cycle. I mean, maybe a fraction of a cycle of light. So it's going to be about a femtosecond. This is typically a couple of femtoseconds for the visible. Now, of course, if you are going into the X-ray regime, and if you are limited by the single cycle, then, of course, you can go into the attosecond and zeptosecond regime. So by changing, this is what I try to express in my talk, by going from the visible to the X-ray and gamma ray regime, then you have the chance really to increase the power because you can make shorter pulses. Now, about human resources. Question about human resources. I think when you have projects which are very, I would say, bold, like what we try to do at Eli, it's not as bold now, but when we started, you know, you have students, you have researchers which like that, you know, and if you really want to make it's important for you to go into a field which is going up like this, and not on a field which is plateauing, you know. And so I don't have many, I think the question of trying to attract students, trying to find all these people coming to run these facilities and all that, I think they will come. They will come, you know. Of course, now with I'm sure with the Nobel Prize, this is really a big statement made by the European community, but they are very interested about this field, and I'm sure this. The students are not stupid, far from that. They understand that. So I think they will be attracted by the facility, large-scale facility, because in these large-scale facilities, they will have really the chance to do absolutely pioneering work. And this, frankly, is what you have to look for if you want really to progress in research. Now, a question of pairs. I talk about creation of pairs of electrons. Of course, at 10 to the 29, the Schwinger field is really, you produce pairs of electrons. And stop at 10 to the 29, because this is really, in order to break a pairs, right, you have to have the field across a Compton wavelength, okay? Because the pairs are basically about a Compton wavelength apart. And the energy that you are going to provide, the work that you are going to provide by this field, has to be equal to 2 times m0 c square. And of course, we prefer to start with electrons rather than with protons. But there is no limit. I mean, we can really produce in a vacuum. You know, you have all the particles, but it will take much more energy to do that. Now, question about relativistic compression. Relativistic compressions, you know, and how does it work? Once again, it's very difficult to do it with your hand. But you can think about, the reason it works is because you have the incident light, which is moving at the speed of light, okay? Now, you have this mirror, which is moving close to the speed of light. And you have the reflected light, which is also obviously moving at the speed of light. And so you end up with a compression. It's very, very similar to if you are, you know, on a beach and you have a wave, and you try to take a scoop. I mean, try to have a scope, you know, and if you have the wave and you start really to move the wave, if your spoon, if you want, or whatever. Move at the speed of the incoming wave, then you are going to have, the wave is going to be stored in the scoop. And this is what's happening in you know, it's, of course, hand waving, but it's what's happening in relativistic mirrors. Now, the question if we had breakthroughs, you know, of course, if we had to have breakthrough to be successful, I would say not really, and I'm going to explain why. Is because when we have the idea, in order to show the basic idea of the CPA, you need, of course, you need a way to broaden the pulse durations, or I'm sorry, to broaden the spectrum of the pulse duration, but I didn't talk about that, okay? So I'm going to make this. So one of the big things in CPA, which really was important since day one, was the question of the gratings, because we were really producing a lot of energy, and we had to compress this energy with the grating, and the grating manufacturer were not, that was a new thing for them, because gratings in optics, they were really dealing with always few photons or photons, not large flux, not large fluxes of photons. And so with this CPA, of course, we came up with a huge flux of photons. So the question is, of course, are you going to damage the grating, yes or no? And so the damage of gratings really came really on the fore very quickly. And but at that time, the gratings were relatively large enough for us, and the energy we had to compress was not big. But then what we had to do is we had to ask manufacturers, and Jobin Yvon in Oriba and so on, mainly. They were the only one at that time. And to make us grating that could withstand, the energy density. And and they did. I mean, we worked together, okay, and they did. We were not using metallic gratings, but we were using holographic grating, and they were very, very good. So holographic gratings, you have dielectric gratings, and the dielectric material has a much higher damage threshold than the metallic gratings. So that was maybe one breakthrough, but they knew how to do it. So it was not so much of a breakthrough, but they did it. They produced very large scale gratings, which could really withstand the fluxes. And the gratings, is always the key, the major problems. The weakness of CPA systems, it's the gratings, okay. But now we have really improved the size of the grating. We can make huge size, meter-size gratings, and with a much better damage threshold. But along the way is when we had this accident where we, in fact, but one of my students had this eye injury, and this eye injury, because he was not wearing his goggle properly, it was not so much a problem because it was not completely his fault, because it was difficult to wear goggles at that time. But anyway, and then we discovered that the damage threshold of femtosecond laser had this unique property to have to not create collateral damage. So basically, we discovered the ideal scalpel, okay, and no collateral damage. So, and that really revolutionized the field of ophthalmology surgery. So that was a breakthrough, but it was not to improve the laser. It was something on the side, but it was a huge breakthrough. I think I answered all the questions.
I think we have still some room for a couple of questions.
Wow.
Well, I don't think.
I think so. I think so. I think so.
Maybe
So
you have one.
It's an opportunity. So only one. He's saying only one. So one question else, please. Please. Microphones. Oh, thank you.
Well, hello, Professor. Thank you very much. My question is Raman effect, does Raman effect takes part in all of this, or if
You are
not...
talking about Raman effect?
Yep, or a stimulated Raman effect.
Mhm.
And if not, it's possible that that could improve the amplification of the compression of the pulse. Thank you.
No, I mean, you are talking about not Raman effect in plasmas and so on. You are talking Raman effect in materials. Not really, because, but it's not a problem because the pulse, even the pulse is very, very long, for instance. You could, this is one of the things we are thinking, of course, about Raman effect in the materials. But the pulse is very long. It's very short when but as a huge bandwidth. Then we stretch the pulse, okay, and so the bandwidth stays the same, okay, but the Raman effect, because the bandwidth is too broad, really, for the Raman effect to take place. This is not the case for plasmas and so on, but in just conventional material. Mm-hmm. Yeah, it's a good question. Yeah.
Thank you very much. So I think we can make an applause to Professor. Thank you very much, Professor Mourou, for having accepted the invitation to share this time with us. To you, thanks, and your wife as well. And thank you, Professor Perlado, for having invited to Professor Mourou. Thank you also to Industrial Engineering School for having supported this. With Pedro as well. So the Institute for Fusion Engineering. Thank you. Thank you very much to the school, Industrial Engineering School, for having supported the invitation and for hosting here the event with Professor Mourou. And indeed, thank you also to the Ministry of Science, Innovation and Universities. So I know that the Minister was very likely to be here, but finally the agenda was not possible. And so we had the DG, who is also professor at the school, and we know she's not missing any meeting here. Anything that we ask her for our university. Thank you very much, Professor Riesgo. And thank you to all faculty, personnel, and students that have made this event possible. And I would like to emphasize that it's a responsibility for faculty of universities to provide opportunities to our students. And this is a major opportunity because you have listened a conference from a Nobel Prize, and you had the opportunity to make questions to a Nobel Prize. So you must thank to your faculty, the school, for having provided you this opportunity. So thank you very much for having provided this opportunity. This is a major opportunity to listen to your conference, to have questions and answers with you. And it's a responsibility from the faculty of university. It's our responsibility as well. Our institution is fully engaged, fully committed with research. And so things like this always help a lot to build Nuclear Fusions Institute, School of Industrial Engineering, and indeed always Universidad Politécnica de Madrid. Thank you, everybody.
Yeah, thank you very much